fresh, basic concept about finite volume methods. Why is that? Because I want to appreciate differences with respect to discontinuous Galerkin schemes. So I will select just a few topics, fundamental topics of finite volume approach. Of course, last week you already had a very good introduction to finite volumes, so I don't need to be detailed. I will just mention what I think is important. And then we will enter discontinuous Galerkin, especially with here the items that you see. And we will end today with the first application, which is represented by Runge-Kutta discontinuous Galerkin. So you know what is Runge-Kutta. We will refresh it a bit. And actually, nowadays, most of applications, also in astrophysics, are done with this Runge-Kutta discontinuous Galerkin. On Thursday, on the contrary, we will introduce an alternative to Runge-Kutta, which is called Eder discontinuous Galerkin, which is based on an entirely different approach and allows you to obtain numerical schemes which are high order, both in space and in time, but with a single time step evolution. So very interesting schemes because they don't have substages of Runge-Kutta. Then I will show you some numerical tests, results that we have obtained recently also. I will show you pedagogically what the advantages of these schemes. And finally, on Thursday afternoon, we will have the tutorial session in which I will guide you through understanding of a code. It is a toy code, but still three-dimensional on Cartesian meshes, and we will see how it works in practice. So let me refresh here the three main numerical schemes we are talking about. Find the different schemes. Let me plot this simple representation in 1D. Suppose you are evolving in time your quantity u, and you have your exact solution discretized over a given grid. In the final difference approach, you have typically at cell center, you define your point values of the exact solution, and your numerical scheme will evolve in time approximation to those. So I'm denoting with these crosses approximations to the true exact solution, right? This is the finite difference approach. Now, let me send it above. We don't like finite difference so much, although it's been very successful. So I send it on top. Finite volume instead still have our exact solution u and our computational grid, but now we are computing cell averages. So for each of these cells, there will be an exact cell average, right? The exact one. Numerical finite volume will evolve in time, an approximation to it. Now I'm exaggerating, but these will be the quantities that we are evolving in a finite volume scheme. It's a cell average quantity. Finite volume schemes have a number of advantages with respect to finite difference. For example, allow you to go to unstructured meshes, which is not trivial. And now discontinuous Galerkin. Okay. Still have our function u, the exact solution, and our discretization. So now we are approximating the exact profile through a polynomial. So I'll draw here, okay, some polynomials which will be given by an expansion or a projection with respect to a basis of functions. So normally, U in the DG approach will be given by a summation, like here in the notes. Actually, I don't need to write it, but and I am writing my unknown function here with respect to this basis of function C. So all the spatial dependence is now in this polynomial basis, and the time dependence is in the expansion coefficients, which are also called degrees of freedom in the literature. So in this new approach, we are evolving in time, and all polynomial is no longer just a point value, and is no longer just a cell average. It's the entire polynomial that is evolved in time, but essentially through the evolution of these expansion coefficients. We will enter into this a lot of time during the lecture, but this is just to introduce the topic. So as I said, I need to recap a bit basic concepts here. So I will start from our preferred formulation, which is the conservative formulation of a PDE in this conservative form, where there is a vector U of conserved quantities and a flux F, typically nonlinear, which depends on the state U. We are in general in three-dimensional space. Now, from 1, you can obtain the alternative formulation 2, which is just written in terms of the Jacobian, df over du, all right? And here comes our classification. If matrix A has a set of real eigenvalues and a corresponding set of independent right eigenvectors, we will say this is a hyperbolic system, which is what we like and we have in several fields in physical science. Physically, these eigenvalues express the speed at which perturbation propagates in your system. So they have a very precise and important physical meaning. So now note please that from 1 you can always obtain 2. So in this sense they are equivalent. But from 2 you cannot obtain 1, in the sense there are physical systems which can only be described by a PDE, still hyperbolic, but not in conservative form. This is called a quasi-linear non-conservative formulation. And it's not possible for such systems to obtain unambiguously a corresponding flux. All right? This is important to stress this thing. So there are numerical schemes specifically for the first formulation, which are different from numerical scheme for the second formulation. Let me show you why. So in the first category, we list all so-called conservative numerical schemes. I will make this notion more precise later. Here you have a number of references. Please note, you find a lot of references in this lecture, but they are not meant to be systematic or complete. You may find something important are missing. They just reflect my background, let's say, so, or what I found it was relevant to me. On the right-hand side, you see there are sources, because typically we do have sources. And these are, so as I was saying, there will be numerical schemes specifically for this formulation. For the second formulation, we have to face a major problem, because it's not at all obvious how to generalize the so-called Rankine-Hugoniot conditions. So for the first system on top, we know Rankine-Hugoniot condition can be written like here. The jump in the fluxes is always written as a multiplication of S, a velocity, the speed of the discontinuity, times the jump in the conserved quantities. It's a well-defined relation through which you can compute the relation through shocks, as you have seen last week for gas dynamics. But if you are starting from a system like this, how will you generalize the notion of the flux? It's not at all obvious. Recently, actually since some time ago already, a new class of numerical schemes, so-called path conservative numerical scheme, have been introduced. And after a phase, I would say, scientific ostracism, now they have become popular and they are recognized to be consistent and very successful. So I recommend also these methods for systems that can only be written in this quasi-linear, non-conservative form. During our lecture, we will talk very little about them because it would require separate treatment, but on Thursday, something will be said. So hyperbolic PDEs in physical sciences are essentially everywhere. I would even claim that at the macroscopic level, all dynamic laws of physics should be written as hyperbolic system. When they are not, then it means that there is some problem, we would say. So, well, classical examples are hydrodynamics, both Newtonian and relativistic. Then MHD, classical and relativistic. Of course, you know that MHD is not, ideal MHD is not strictly hyperbolic because Stokes' theorem is also involved in the induction equation, not only Gauss' theorem, but still we can classify them in this category of hyperbolic PDE. The relativistic but resistive MHD is also in our list, and here you have an extended set of variables because you have to evolve in time also the electric field, not only the magnetic field. Relativistic dissipative irreversible thermodynamics, so with dissipation included, non-perfect fluids, is also a very interesting example. And in the last year, starting from old papers providing hyperbolic formulation, in the last years there have been a lot of progress for providing suitable numerical formulation. I still think that is not totally satisfactory what we have now, but the field is improving. Radiation hydrodynamics, of course, is another example. You will have a lecture on this, and it's an extremely interesting field of astrophysics. Outside astrophysics, I can mention linear elasticity problems, hydrodynamical modeling of semiconductors, all systems that can be written as a hyperbolic system of PDEs. Even Einstein equations, no? It's true that nowadays the majority of numerical relativity code is based on second order in space formulation of the Einstein equations, so not first order formulations. But the hyperbolic formulation, first order hyperbolic formulation, is also very promising, and as you have seen last week in other lectures. I need to say something about the finite volume discretization, as I said, because we want to make comparison afterwards. So in one spatial dimension, identifying our cell, ij, from j minus 1/2 to xj plus 1/2, we can integrate in space and obtain this relation here, starting from the conservative formulation in strong form. I'm neglecting sources for the moment, no, but we will recover them after. So here on the right-hand side, you have the flux difference, the well-known thing, and here there is still time derivative. Now we integrate in time, and we get the second expression here, where there is a u integrating at time level Tn plus 1, and here on the right-hand side at the previous time level. Now you can define your cell average, which is really a cell average, volume average, and a numerical flux, which is an average in time of a flux, which is computed at the interface between adjacent cells. So this is the definition. With this definition, you can obtain such a reformulation, but it's not yet a numerical scheme, it's just a rephrasing of the same stuff. It's not, we have done nothing numerically, this was mathematics, integration and definitions. So this is, however, the starting point, because as soon as we give a prescription for the computation of these fluxes, we will obtain a numerical scheme, and also for the cell averages. So this formulation, which is not yet a numerical scheme, becomes an approximate numerical method, finite volume, when we give an approximation for the computation of the fluxes. And you understand that the computation of these fluxes can be problematic because they are at the interface of two cells. So they will depend on quantities from the left and from the right, which are in general different. So how do we, this is the old business after all, how do we compute a consistent flux? High resolution shock capturing schemes are in fact numerical schemes, finite volume numerical schemes, in which these numerical fluxes are computed through the solution of a Riemann problem. And this is the old idea of Godunov, no? Introduced already in 1959. Actually, Godunov method, it's the first order method, is the first of these high resolution capturing schemes. You have already talked about Riemann problem a lot last week. I will not say much. I just need this slide to refresh our minds. From a mathematical point of view, the Riemann problem for a general nonlinear hyperbolic system for us is an initial value problem with very simple initial condition given by these constant values. U left, call the U left, and U right. And you have such Riemann problem at each interface of your numerical domain. So here, at every interface, xj plus 1/2, you will generate a Riemann problem because you have jumps from the left, on the left and on the right. Depending on the complexity of your PDEs, you will have a bunch of waves coming out, refraction wave, contact wave shocks. In MHD, you have many of those. And you need to solve a Riemann problem. Of course, we don't want to use the exact solution of the Riemann problem. This would be computationally too expensive, even for gas dynamics, for classical Euler gas dynamics. So what is done typically is adopting an approximate Riemann solver. You have also, you know about them from last week. There are several. There are those involving just eigenvalues of your PDEs and those involving eigenvectors. So in our code on Thursday, we will use a very simple Riemann problem. So it's not my topic here to talk about Riemann solvers, sorry. But it's important to know that they can be very sophisticated, particularly those using eigenvectors. I said at the beginning we need to make the notion of a conservative numerical scheme a bit more precise, because there is then something to stress. And in fact, we can say the following. Conservative numerical scheme must be based on the conservative formulation of the equations. And we require two things. First one, the numerical flux at each interface must depend on values of the quantity U in neighboring cells. So it can be a number of cells involved. And the second is just a sort of consistency condition. If the quantity U is constant and is plugged into this numerical flux function, it must give you back the physical flux. All right. For example, note that the Riemann solver flux, which involves just the left and the right states, is actually fulfilling the first condition and also the second one. And so our Riemann solvers are indeed providing an example of conservative numerical schemes. Let's say are a building block of our conservative numerical scheme. Why mention this property? It's not just for academic. Because conservative numerical schemes, according to this theorem proved in a long time ago, if convergent, because they may not converge to the weak solution of the problem. I will say something about the weak solution in a second, but this is a positive result as it stands, right? They converge to a solution, the weak solution. But if they are not conservative numerical schemes, so for example, numerical schemes based on artificial viscosity, then we are in trouble because they do not converge to the correct solution if there is a discontinuity in your flow, such as a simple shock wave. And this is a problem. Maybe it can capture rarefaction waves so well, but the velocity, the speed of shocks will be wrong. And you don't realize if you don't have a comparison with other methods. So discontinuous Galerkin method will be conservative numerical schemes. This is important. I mentioned these weak solutions, so because weak solutions and the weak formulation of the equations is also involved for discontinuous Galerkin, as we will see, let me introduce this machinery. We start from the conservative formulation in 1D. I'm neglecting sources, and I multiply it by a continuously differentiable function, psi, right, from a given functional space, and it has compact support. Then I integrate in space and in time, as you see here. Now I take integration by parts, both in space and in time, so that I shift derivatives on the test function psi. You see all the derivatives here, partial t, partial x are acting on psi, while here I have the so-called principal parts, which are computed in these intervals. Now, because psi is a compact support, it will vanish at spatial infinity and also at temporal infinity. So you have this property 15. And out of these 4 terms, only one will survive, which is this on the right-hand side, and is the one computed at time level time t equals 0. And so when you get this relation, you say, all right, my solution U is a weak solution of the conservative equation if it satisfies this equation for any function psi, continuously differentiable with compact support. Is it this important? Yes, because at discontinuities, for example, strictly speaking, you cannot find a continuous solution of the strong formulation of the PDE. It's discontinuous. But still you can find a weak solution which satisfies this relation and will be your solution. Actually, computationally, you could even find more than one weak solution. And so you need a guiding principle for excluding the unphysical ones. So the guiding principle will be based on physical entropy condition, after all. Okay, it was important to introduce this the technology because it will become very standard for discontinuous Galerkin, which is actually a weak based on a weak formulation of the PDE. So this is also for me to introduce you the transition to higher order numerical schemes, and so I need to mention the Godinus first order method. It's very classical and simple, but it's worth mentioning. In the Godinus first order method, at each interface between adjacent cells, we are assuming that the left and right states of the Riemann problem are just given by the constant cell averages. So it assumes a piecewise constant approximation within the cell. Is this green line here everywhere, and gives you, you see here, uj and uj plus 1 are the left and right states. So this is, if you do the analysis for a linear equation, for example, linear advection equation, you will immediately see this is only first order accurate in space and time. But we want to go beyond first order, of course. And so first of all, we define our error. We have a local error here, which is the absolute value of the difference between the exact and the approximate solution. It will contain typically the summation of 2 terms. The first one related to space approximation, the second to time approximation. We can even define the order of accuracy of the global numerical scheme as the minimum of these exponents. You know? And we want to reach high exponent in principle, not just first order. Is it really worthwhile doing this? Can't we say, well, I like first order schemes, I will refine my grid as much as I can, extreme refined meshes, and I don't care about anything else. Well, you can do that, but it has already been shown that if you set an error that you tolerate in your calculation, it is much more computationally efficient to go to higher order schemes with a coarser mesh rather than first order or second order scheme with extremely refined mesh. So this is the motivation for going to higher order schemes, because it becomes computationally inefficient as you refine the mesh. In the rest of our discussion, we refer to higher order methods starting from order 3 for convenience, all right? You know already from last week that when there is a discontinuity, locally there, your numerical method will be just first order accurate, all right, if there is a shock wave in your solution. But we are talking about smooth solution for the moment. So we want to go to higher order, and unfortunately there is another theorem due to Godunov again, and it says the following, that a linear with constant coefficients and monotonicity preserving scheme is at most first order accurate. So let's see what it means in practice for us. Monotonicity preserving can be regarded as a synonymous of non-oscillatory. You know? It says that if you have a given monotonicity at time level Tn, this will be preserved at any future time. So you will not create new local minima nor new local maxima, so your numerical scheme will not oscillate, which is a very nice property. The second requirement is that numerical scheme is linear, meaning that the solution at time level n plus 1 can be written as a linear combination of the solution at previous time step with this constant bk. Now, this is a linear scheme. For example, if you write the Godunov method, first order, for the linear advection equation, it will be a linear scheme. But we want to go to higher order, so which of the two should we sacrifice? We don't want to sacrifice the monotonicity preserving property because we don't want to introduce oscillations. So we will sacrifice the linearity of the scheme, all right? Conclusion, high order schemes, even second order, must be nonlinear. This is a very important result, though simple. Let's see, how do we see nonlinearity in a typical finite volume scheme? You are maybe familiar with total variation diminishing schemes. Just may recall you the definition of them. So the total variation of your numerical scheme will be the summation of these absolute values of the jumps. So this is defined at generic time level Tn, and you want numerical schemes that keep this quantity finite are called total variation diminishing. Actually, they have this property. It remains bounded. An example is given by the famous mean mode finite volume scheme, which provides you a simple spatial linear reconstruction in each cell. I don't know if you are familiar with it, but you have to prescribe this simple linear reconstruction relation for each cell. And what is the nonlinearity of the scheme, which allows, in this case, for second order accuracy, is hidden here in the slope, because the slope sigma is not a constant, but it depends on the data. Because if you look at the definition of the minimum modulus function, is this one. You take exactly the minimum, you select the slopes with a minimum modulus, comparing from the left and from the right. So for example, when I reconstruct for cell J here, I have to compute the first slope here, and then the second, and you select the minimum modulus one. And you say that this is your local spatial reconstruction. So because this sigma depends on data, here you introduce nonlinearity, and your scheme is actually second order in space and non-oscillatory. Similarly, you can build a lot of numerical schemes, finite volume, which are nonlinear. All these one essentially non-oscillatory, weighted essentially non-oscillatory schemes, always are built on this strategy of reconstructing a data representation of the solution for each cell, which depends on data in neighboring cells. All right, so this is a simple remark that I mentioned at the very beginning. It's just for your knowledge. Remember that up to second order, finite difference and finite volume numerical schemes are essentially the same. Because why is that? Because the point value representation up to second order, which means up to a linear representation within the cell, coincides with the cell average, no? Because of the trapezoidal rule. So finite difference and finite volume are the same up to second order. I need two last concepts about finite volume, then we will enter the discontinuous Galerkin framework. And the two last concepts are the method of lines that you possibly are already familiar with. We need a strategy for solving in time our hyperbolic system. So you can keep a continuous representation in time So I keep here the time derivative on the left indicated, while on the right I have the spatial discretization written. So there is the flux difference here. Now you can compactify these operators in the term Q, which contains the sources and the flux difference, and then you have an ODE to solve, right? This is a starting point of so-called multi-step Runge-Kutta method. And typically what they do is they start from the first order Euler integration in time, and then they correct it through a sequence of substages. So in general, there will be here a prescription for any of these substages. You start from U0 at time level Tn, and you have a number of such substages with constant coefficients here to be specified, alpha and beta. Note that this is an explicit scheme because the summation here stops at I minus 1, while here there is I, so this is explicit scheme, which is enough in most of cases. So examples are Runge-Kutta second order and Runge-Kutta third order. I'm just mentioning U for you. So in both cases, you see there is the first order Euler integration and then the correction. Remember, there is also an implicit version of such schemes. They are called implicit explicit Runge-Kutta, IMEX Runge-Kutta, and they are the necessary choice when your sources become stiff, okay? As you have seen above here, in general you have sources, and sources can become stiff. We will make this concept much more precise on Thursday. Today we don't talk about stiffness. But in any case, Runge-Kutta are successful in both circumstances. And all right. Last one is very simple for you, is the CFL condition, which I just need to mention because there will be an important comparison with discontinuous Galerkin. So the CFL condition is a necessary condition. It's not sufficient. It's not enough to have it. And it tells you that the so-called numerical domain, the domain of dependence of the solution, which is a physical domain of dependence, must be contained within the numerical domain of dependence, which is entirely dictated by the stencil that you are using. So for example, this is a CFL stable scheme because the green area below, which is the numerical domain of dependence, includes the true domain of dependence. So any point J here can only depend on a point in the orange area, and this is a CFL stable scheme. On the other side, you have an example of a CFL unstable scheme. You can also rephrase this in terms, of course, of the eigenvalues, because the slope of this numerical domain is dictated by the eigenvalues. And so physically, you want that the maximum possible eigenvalue is smaller than delta x over delta t. And this gives you the celebrated CFL condition. So everywhere you have your Riemann solver implemented, you must take care of computing correctly the maximum possible eigenvalue, or at least an approximation to it. All right, we have introduced all what I need for now our transition to discontinuous Galerkin. So these methods require a little of introduction. They can be considered as a numerical methods for the weak formulation of the equations. We know already what is a weak solution, so at least we can understand this sentence. And they were first applied to first order equations a long time ago for a neutron transport equation. However, their application to hyperbolic problems in general has become possible only after the early 90s due to these important contributions. In this framework, we are, as we said at the very beginning, we are evolving in time the coefficients of an expansion with respect to a basis. And so we don't have any reconstruction operator. We don't have, like in finite volume, we don't have to reconstruct a profile within a cell because we already have a polynomial within the cell, which is the discontinuous polynomial. This feature is in common with finite element method that has been used for a long time in engineering application. However, unlike classical finite elements, numerical solution given by this discontinuous Galerkin scheme can be discontinuous at interface between elements. No? This is important for us because in general we will have discontinuities, so we don't want to impose matching of polynomial at boundaries. That's why we talk about discontinuous Galerkin, right? So this is a key point, and it will be reflected in the fact that Riemann solver will still be there. So discontinuous Galerkin scheme will include Riemann solvers, as we will see. So here we mention only because my major field of applications is relativistic astrophysics. The implementation of discontinuous Galerkin in relativistic framework has been done in the last 10 years or so. There are not many contributions, but the field is moving, even for the solution of the Einstein equations, and so they are regarded as very promising. What are the advantages of these schemes? Well, there are many. The first one, when you implement a discontinuous Galerkin scheme, and you do once, then you can change the order of accuracy by simply acting on the degree of the polynomial. And this is a nice feature. You don't have to implement a different numerical scheme at each order. For example, finite volume, you may have your preferred third order scheme, a PPM. Then you may have a Wien of 4, MP5, there is a large zoo of schemes. Here, you have a single scheme, very flexible. They allow for dynamic HP adaptation. So it means that during the computation on the fly, you can change the mesh size H and the degree of the polynomial. They incorporate Riemann solver, so they keep the properties of upwind conservative numerical schemes as we wish, and shock capturing. And because they do not require the introduction of stencils or reconstruction stencils, they also imply a reduced amount of MPI communication in your code. You don't have to transfer data from cell to another. This is important. Well, for astrophysicists, this is not so important, but they can be extended to general unstructured meshes. In some cases, it could be relevant. In some fields of application, it's extremely relevant. And you cannot do this with a finite difference scheme. You can do with a finite volume, though, yes. Robustness of the scheme. This is related to a property we will prove later today. They are L2 stable, as we will show. So they are typically robust on smooth solution. And they have this spectral convergence property, which I showed you through just a plot. This is computed by our group in Trento. So you can fix, you fix the resolution of the test, it's a smooth test, and you increase the degree of the polynomial, no? From 1, second order scheme, to 8, which is not small. And the error on this logarithmic scale is decaying linearly. So it's an exponential decay of the error. And this is the notion of spectral convergence, which is typical of these methods. Spectral methods in general allow you this. The spectral methods have been used in astrophysics since a long time, including relativistic framework. There are also some drawbacks. It's not only positive things. So first of all, if you may think they require change of philosophy, you are no longer, you have a quite different code in front of you. You're not evolving in time point values or cell averages. You have these polynomials to take care of. All right. Then second, they are constrained by more severe CFL condition, and we will see it in a while. And the third one, this is maybe the most serious one, they require some spatial procedure to avoid oscillations. Why is that? Because in the definition of Godunov theorem, these are linear schemes. And so they are linear, but high order. So they will oscillate, right? If you don't do anything, they will oscillate at discontinuities. And so something should be done. Now we go into the DG discretization, the discontinuous Galerkin discretization. We have our starting PDE system in conservative form, as usual, with no sources for the moment. And we are in three-dimensional space in general. Now, as I already written at the very beginning, we expand the solution with respect to a given basis. This is a CL polynomial from 0 to m, right? Which are our degrees of freedom. All right. Now, we multiply the equation, the starting equation number 30 here, by the test function psi, which belongs to the same functional space of the basis. We multiply it and we integrate in space. So here is what we get. All right, you see multiplication and integration over the cell. Now you integrate by parts in space. So what happens here? You generate a term which has a divergence of CF. Apply Gauss theorem, it becomes a surface integral. And here there is C, K, F computed through a flux. Minus this extra term, which contains the derivative of the test function. And this is a volume integral. So this is the starting point or the prototype of the discontinuous Galerkin discretization. Because you see the difference with respect to finite volume. There is this time evolution, yet multiplied by psi, of course. And there is again a surface integral, like in finite volume. And there is therefore a flux to compute at the surface. This will bring in Riemann solvers. So Riemann solvers are still included in the scheme, exactly here for the computation of the second term. Then there is minus a volume integral. This is completely new with respect to finite volume. You don't have such term, of course, because there is no psi multiplication. So here is what I was saying, the importance of having, again, Riemann solvers included. The CFL condition for this continuous Galerkin scheme is unfortunately more severe than for finite volume. And here, actually, the mathematics become very heavy, and I found two different results in the literature. There is the first one, which says that delta t is constrained by h, which is the typical mesh size. We can say this is just delta x over lambda. We know this from finite volume, but now there is division by the factor 2m plus 1. And m is the degree of the expanding polynomial. So this is bad news because we are dividing by 2m plus 1. And as we increase the order, we are more constrained in time. There are other papers around, especially the first one. They show that delta t should be constrained in this even more severe way in order to guarantee L2 stability. All right, so the analysis is complicated, as I said. Typically, especially in the first case, it requires the solution of a numerical von Neumann stability analysis. So we don't need to say much about, but in our experience, in our application, the first condition is enough to guarantee stability. So in the code we will test on Thursday, we will find this first implementation. Yes? Okay, look at the first one. You have to look for the maximum eigenvalue of all over the grid. And then you prescribe a single time step. But let me go, because your comment, I think, is related to what I'm saying in a second. There are two ways out of this severe condition. The first is to increase h as much as you can, right? It's in a high order scheme, so as I said at the very beginning, there's no point in keeping h too small. We want to allow for h large. And this is so the first solution, at least a way out to the problem. The second is maybe related to your question, is local time stepping. So you can allow any cell to march in time with its best time step. And this is, of course, requires you an spatial implementation. Technically, it's not so easy, but is very convenient, especially if your complex structures in the flow are formed only in a few places, right? It's limited in a few places. You can find actually in the book here from Hesthaven, you can find details about local time stepping. I will not talk about it. Maybe on Thursday we can say something, but it's out of the scope. So now we need to say more about the choice of the basis function, right? In principle, you are totally free. You can choose your preferred basis of polynomials. But in practice, there are better choices than others, of course, as usual. A first class of bases is represented by modal bases, or also called hierarchical bases. So when you fix the degree of the polynomial to m, they are formed by m plus 1 polynomials from degree 0 to m, right? So that's why it's called hierarchical. And Legendre polynomials are a typical example of them. Legendre polynomials are very well known in mathematics. They are obtained from an eigenvalue solution of an eigenvalue problem of the Sturm-Liouville problem. And for example, in the reference element from 0 to 1, you can compute your shifted Legendre polynomial in the following way. And for example, if my degree is m equals 3, so I will have 4 polynomials, C0, which is just a constant one, up to C3 of degree 3, okay? And at least once in life, you can look them at this polynomial in your reference element. Yes?
So if we take the finite volume scheme, and suppose if we introduce a polynomial fit at every cell center to match the next two, and we can choose a higher order polynomial, say suppose any higher order. What is the physics in the problem that dictates whether we should go to these kind of schemes instead of finite volume with a high polynomial fit?
Sorry, what is the physical?
So what kind of problems should we, what is the physics in the problem
Yes.
that actually would motivate
Yes.
to go to these kind of schemes instead of finite volume with high order polynomial?
Okay, also for finite volume, you can have your polynomials reconstruction, and this is perfectly acceptable. Here is a different kind of scheme. So as I said, for example, you want to avoid reconstruction involving cells, adjacent cells. So you have a single cell with its own well-prescribed polynomial, which does not depend on adjacent cells. But we will see something more later. Another possibility, alternative to the modal basis, is represented by this nodal basis, which is actually what we will see in the code on Thursday. So in this case, we still have fixed the degree of the polynomial to m, and there are m plus 1 such polynomials, but all of degree m is not hierarchical. How do we build it? We consider our reference coordinate c from 0 to 1, which is a mapping from the reference space to the physical space. So here in Cartesian coordinates, which is very simple, it says that the physical x is given by the left-hand side coordinate of the cell plus c delta x, right? Now you can compute the so-called nodal coordinates. They are m plus 1 points from 0 to 1, which are the zeros of the Legendre polynomials of order m plus 1, right? So there are Fortran routines for this that just give you the zeros of such polynomials. They are coordinates. Now you can compute, you can perform a Lagrange interpolation through such points. We know how to do Lagrange interpolation. And we will obtain a basis of polynomials, all of degree m, with this nice property here, equation 40. So they satisfy this Kronecker delta condition, which means that the first, because by construction essentially, the first polynomial of the sequence computed in the first node will be 1, give you 1, computed in the second node and the third node and so on, give you 0, right? Let me show you an example of such polynomials. Order m equal 2, they are parabolas, and there are m plus 1, so 3 parabolas forming your basis. You see the first one is the red. Here you have the blue dots, which are the nodal points, the coordinates of the nodal points. In the first node, first polynomial is 1, while the other two are 0, right, because of the property of the Lagrange interpolation. In the second node, you have the opposite position, is the second polynomial, which is 1, and the other two are 0, and so on and so forth. This is called the nodal basis. In the programming practice, you can either implement directly the Lagrange interpolation, or maybe even more conveniently, you can do in this way. Let's take this example with m equal 2. So we have parabolas again. We have 3 parabolas with coefficient a, b, c, a prime, b prime, c prime, a second, b second, c second. And so you see the condition here. The first parabola computed in the first node will be 1. A plus big C1 plus C1C, sorry, C1 square C will give you 1. The first parabola in the second node will give you 0, and so on and so forth. So by simply solving this linear system, you will get the coefficient A, B, C, A prime, B prime, C prime, A second, B second, C second, which are your unknown polynomials. So you build your basis, all right? And this is what we will see in the code. Once in life, as I say often, we can look at these nodes. So m equal 1, 2, and 3. The table was very long, so I cut it, but you can go on. You can compute your nodal points, Gauss-Legendre nodal points, and the corresponding basis function. Okay. There is also a nice property related to this nodal basis, and is the following. When you compute an integral of any function, with the discontinuous Galerkin, as you have seen, there are integrals to compute, we will use a Gaussian quadrature rule. So we will expand this through this relation where we have Gaussian weights, omega k, and g, the function to be integrated, evaluated at the nodal points. Now, if you have a nodal basis and you expand g with respect to such basis, you will exploit the nodal property. So this relation will be very simple because you have the delta Kronecker coming in. Moreover, this Gaussian quadrature is known to be exact for all polynomials up to degree 2 m plus 1 nodal points minus 1. And this is very nice because it says that we are not losing accuracy because of this Gaussian quadrature relation. The order of accuracy is entirely dictated by the degree of the polynomial. You are not losing anything by performing such integral. Now we come to this very nice property of discontinuous Galerkin methods. They are non-linearly L2 stable. I give you the theorem, and then we will show at least once in life the proof of it. But we can get the theorem first of all. So it says the following, that there is a discrete cell entropy inequality for the square entropy. So numerical analysis people like to call entropy what is actually not an entropy, but this is a relation that is satisfied. That during the evolution, the time derivative of this spatial integral will not grow. You already understand that this is a nice property because the square of this u will remain bounded. So this is called the L2 stability property. And this property makes discontinuous Galerkin scheme very robust, especially for smooth solution. Especially even if you have strong vorticity problems, turbulence, whatever, as soon as you don't create shocks, because then it's another story, discontinuous Galerkin will typically perform better than finite volume, which do not have such property. Unfortunately, this L2 stability is not enough to prevent oscillations at shocks. As we said, discontinuous Galerkin, according to Godunov theorem, are linear schemes, so they will oscillate at discontinuities. And they are not L infinity stable, which is the property that should be imposed to have stability even at shocks, no? But they are L2 stable. Okay, so as I promised, I will show you the proof of the theorem. So the font now reduces a bit because it's a 3-slide theorem, but at least once in life it's good to see the proof. So we start from the conservation law again without source terms in one spatial dimension only. Okay? F is typically a nonlinear flux, so it's not just the linear advection equation. Now, the bad thing about these theorems is in many cases they are proved just for the linear advection. This is a general nonlinear program. So now we need a couple of definitions. The first one, you can define the square entropy, which is this U square half, and the associated entropy, so-called entropy flux, which is this F2, calligraphic, UFU minus integral of FU in the space U. Okay, definition. Second definition, we call we call an efflux a Lipschitz continuous function Fi plus 1/2, which is a function of the two states, U minus U plus, if it fulfills this consistency condition, which is natural, we already seen a consistency condition for conservative schemes. And moreover, the second one, it's a bit more, this is a novelty, it's the integral from u minus to u plus, the two states. And so the difference fu minus this efflux must be positive when integrating over u, okay? Definition. Now we assume that u belongs to a functional space Vh, as it is an approximate solution of our PDE. So it belongs, Vh is included in L2. Now L2 is a functional space of function with a two-norm bounded, finite two-norm, defined in this way. So it's the set of G with this property here. Now we multiply by the equation 43 above, which is our governing equation, by this phi. And phi belongs to the same functional space. It's important. So the solution expanded over the basis belongs to the same functional space of the function by which we multiply. Okay, so this is the discontinuous Galerkin procedure that we have already written above. So there is this term, the first one, then there is the flux difference minus the volume integral with the derivative shifted on phi, where here I am integrating over the cell, single cell I, and I have here an efflux, so the flux here must obey the two conditions I've described in the previous slide, must be an efflux between I minus 1 I, and the second flux is an efflux between II and II plus 1. Okay, now, actually this is the theorem, and our result will be a corollary of this. The numerical solution U of the discontinuous Galerkin scheme 47, this one, the numerical solution of this one, in which Fi plus 1 half is an efflux, obeys this discrete cell entropy condition. You see, this is just over the single cell, not over the whole space. The integral is this term plus this difference is smaller than 0. From this, we will get the celebrated L2 stability condition. So the proof is this. Both U and phi belong to the same functional space. This is the key point of discontinuous Galerkin. So we replace phi here in 37, the previous equation. Rather than phi, you can write U, because they belong to the same functional space. If you do that, you can integrate the first term. You see here where the derivative of u square half comes from. And then you have plus. You see above there was phi. Now there is u here. Minus integral fu dx u, not phi dx equal to 0. Now here is just a matter of rewriting a bit, because this integral in space can be converted in integral in the u space, like here. And we are integrating, as you see, from ui minus 1 half on the left-hand side of the cell to ui plus 1 half, the value at that point. And here you introduce the primitive of fu, which is this g, so you can write it like in 50. Now, we go back to equation 49, which is this. We have rewritten this term here in this way. Now G has been introduced. You see here these terms. So far, so good. Now we just subtract and sum these two contributions. You see, so the first line is exactly the same as this. Now for the second line, we are just putting a minus and a plus of the same quantity. Okay, and so after all, we can write equation 53, in which we have defined this f-hat contribution, which is computed at I plus 1 half quantities, fi plus 1 half u I plus 1 half to the left minus g u I plus 1 half minus. And correspondingly, there is an f-hat I minus 1 half, which comes from here. And finally, there is this r-hat, which is what we added and subtracted here. All right. So now we obtain almost the result. we notice that these terms f hat are the discrete entropy fluxes that we defined at the very beginning. We defined the continuous version of them. The discrete entropy fluxes are, sorry, the continuous entropy fluxes are this. And now we have a discrete version of them, which are here, which are these. Sorry, f hat, and they are here, right? While the term r hat can be written in this form. You just go back here to see equation 56 can be written in this form, equivalent 57. And now we have obtained a relation which is valid just for the single cell over which we are integrating. Because we have this property of the efflux given by equation 46 above, which is this. This is always positive. You see, it was positive. And now we have such term in the equation. So this is always positive. Sorry, I went too fast. It was here. Here, equation 53. This one is always positive. And so all the rest must be negative. And so you get this conclusion. Now you get the final result. If you integrate it over all the computational domain, the summation of all these terms will cancel. If you use boundary periodic conditions, then everything is fine even at the border. And you get the result, the final result, the so-called L2 stability condition. The time evolution of U square half integrating over the whole computational domain does not grow. Just a comment, this result is valid for any nonlinear hyperbolic PDE, which is very good. And there is also a measurement of the numerical dissipation that we are introducing. Because this term here, R hat, equation 57, actually gives you a measure of the numerical dissipation. You see that it depends on the jump, because we are integrating at the same local position, but values computed from the left and from the right. So as you increase the jump, you increase the numerical dissipation. All right. Unfortunately, as I said at the beginning, this L2 stability condition is not enough to prevent appearance of oscillations. So something more should be done. Now we enter essentially, this is the last topic of today's lecture, is Runge-Kutta discontinuous Galerkin. And we want now to generate a numerical scheme and show how to integrate this in time. We have our discontinuous Galerkin discretization already written above. Again, you see here there is the term with the time derivative. Here there is the surface integral with fluxes at the surface and minus volume integral. We expand now the solution UH of the basis, and we know how to do it. And we replace this into the UH. So you get this summation. You see that there is summation over the index L, and there is CL, the U hat L over the T. So there is a time derivative for each degree of freedom. Now, in one spatial dimension, this is an example in 1D, the flux integral is just the difference at the two sides of the cells with this multiplication, CK, F star. Star because I rephrased the whole computation on the reference element, okay? It's not, this is the physical domain, this is the reference domain. Minus integral of here, there is the spatial derivative times the flux. So here there is no Riemann solver to introduce because our flux is computed within the cell, while here there is a Riemann solver involved. So here the advantage is this, you can compute these integrals analytically, you know everything about your basis, so you don't have to worry about it. And so you can now decide your order. Let's do an example. We fix m equals 3, so cubic. And let's use a modal basis for the moment. It's pedagogically instructive. So we use a modal basis, and we write it u as this u hat 0, C0 plus u hat 1, C1, plus u hat 2, and so on. You replace that, and you get a system of ODEs to solve for each of the degrees of freedom, all right? Because here you exploit the orthogonality properties of the integrals, so you get an equation for each of them. And this is the ODE that you want to solve. It's nonlinear, is a couple ODE, because each of the degrees of freedom is implied in the computation of the fluxes, so you have to solve it all at once. And when you do this, you can do Runge-Kutta time integration, as we have refreshed before. So this will generate a class of numerical schemes which are called Runge-Kutta discontinuous Galerkin. And they are essentially in one spatial dimension given by this formulation. So let me comment a bit about them. Here I have chosen a modal basis. Why did I do that? Because the first degree of freedom, the first coefficient, as you see, evolves in time according to a finite volume scheme. So at first order, it's just like a finite volume. It is intuitive. You can see this only for a modal basis, because the first polynomial is just the constant 1. And so the expansion with respect to the constant 1 is the cell average. So here you recover finite volume. And then you have corrections, essentially, to take care of. The values of the fluxes at the cell borders can be obtained by solving a Riemann problem. So we incorporate this upwind property into this Runge-Kutta discontinuous Galerkin. And at least in principle, solution of such Riemann problems does not require any spatial reconstruction, which is good. Usually, when you solve a Riemann problem in finite volume, you have to do a lot of job for reconstruction, the left and the right states. Here you don't have, because they are already given by the G polynomial. But there is a problem, we will see this on Thursday, that you generate, you have to do something to avoid the appearance of oscillations. Now, in the astrophysical context, but not only in astrophysical context, the majority of discontinuous Galerkin scheme adopt this Runge-Kutta discretization in time. There is an alternative to this, and I will talk about it on Thursday. I prefer to split a bit, because on Thursday we will also go through the code which adopts the second formulation. So if I show you the formulation today, then on Thursday it will be a bit late. And there is also, however, a problem with Runge-Kutta discontinuous discretization, because when you increase the order a lot, then you have a lot of substages. So this is called the phenomenon of Butcher barrier. The number of intermediate stages become larger than the formal order of accuracy. If you want to do a Runge-Kutta order 5 or 6 or 7, this is the problem. And so this then becomes very time consuming, because you have to do MPI communication for each of the substages, and it's not a good choice. That's why we will propose an alternative to Runge-Kutta based on this Eder approach. And that will give us a numerical scheme that is a single step in time, but still high order, both in time and in space. I was a bit faster than I expected, and so actually I stop here, and if you have questions, we can take advantage of this extra time. Thank you.